So our first scenario is fairly straightforward. It covers off on a pedestrian approaching a static vehicle. And there's a couple of variations to this particular scenario. There's one where we're approaching a vehicle that's in a safe state. And then there's a second one, which I'll take you through in a moment. But in the one that we're approaching in a safe state, it's probably important we talk about what safe state is first. Safe state is basically where that machine is safe to approach. It has to be defined by the operation, but typically you would have something like the park brake on, the engine in neutral, or maybe even in park, grounded tools, whatever it needs to be to feel that you're safe to approach that vehicle. So here we have a pedestrian approaching a safe vehicle, and there is a operator in the cab of that vehicle. That's really important to understand in this particular example. So as that pedestrian's approaching, let's just assume that the operator is unaware that there's a pedestrian there. So we get our A1 awareness on the screen, and if the operator doesn't look at that screen or is not aware of that pedestrian and takes the machine out of safe state, so puts it in gear or takes the park brake off, immediately we get that A3 alarm, that high level alarm to indicate that the operator, that there's a serious problem that needs to be addressed before any further activity occurs. So that's our first variation of a static vehicle. The second one is where the pedestrian approaches an unsafe vehicle. So this machine is prepared to move. And if that pedestrian continues to approach, so we get our multiple alarms. So we get our A1 to begin with, we get our A2, and if the pedestrian continues to approach, we get our A3. So there's various examples of where these two apply. Probably the big one, the easiest one to understand is go lines and around parking bays and workshops, where you have a lot of machines and humans interacting, particularly at the start and end of shifts or during crib breaks. You have a lot of that interaction, and you'll have a lot of different states of the machines. You'll have some machines parked up in that safe state, and you'll have others that are either trying to move or have just come in and haven't finished parking up. So it's a pretty important sort of scenario to understand. However, there are potential for false or failed alarms to occur. And in the next slide, we capture some examples of those false or failed alarms with pedestrians around those vehicles. So in the top left, a classic one that we've heard in the industry is the multiple pedestrians inside the vehicle. So they're sitting in the vehicle. However, the system thinks that one or more of those people are actually outside of the vehicle, and therefore it alarms and creates an alarm there. The next one across to the right of that one, we've got multiple passengers inside the vehicle, and we have a pedestrian immediately outside the door, possibly leaning in the window, having a chat. And the system thinks that person, because they're so close, is actually inside the vehicle, and we have no alarm generated. So these are the examples of a false alarm or a failed alarm based on those sort of circumstances. And there's lots of real world examples of that. So if we go back to our go line example, if you look at the bottom left, we've got pedestrians moving around our vehicles. So they could be quite close, so they may not be detected. And this is a sort of classic example of what needs to be considered. The other quite important one, particularly in the underground space, is where we deliberately have activities that require pedestrians to be in close proximity to moving machines or machines that are active. A great example is an IT, or an integrated tool carrier as they're called, which is a tractor, an articulating tractor with a basket on the front. So you'll have someone in the cab of that tractor operating the vehicle, and then you'll have people in that basket. And sometimes in certain circumstances, depending on the job, you may actually have a person on the ground assisting, whether they're a spotter or they're managing another aspect of the job. But you do have people around a machine, and that's something that needs to be considered as part of the industry-wide design process. Another example is where we've got someone that could be under the machine. Sounds a little bit unusual, but there has actually been circumstances where someone has been under a machine. And we also have an example where a pedestrian could be invisible to the system by being inside of the articulation point. So being really close into the body of the machine. That, as anyone that's aware of loaders, that's actually where the main door is, the door access to get into the cab. So stepping inside of that articulation sometimes can possibly render you invisible to systems. So these are examples of a scenario that we know is a problem underground that we want to address with possible technology, but we're also aware that there are possible limitations or concerns around trying to address that. And this is what I was talking about, where we're trying to define the problem for the industry to ultimately try and solve, right? We want to work with the industry to try and solve this problem with our different suppliers. So this is what we're trying to define. Now, if we move to scenario 2, we've got our vehicle moving towards an object. So on the right-hand side, we've got our loader in this particular case, and that loader is going to be approaching the LV or pedestrian on the left in this particular example. So as that loader approaches, they should have their A1 awareness on screen. So they should have their situation awareness in general. If they get too close, they get their A2 alarm. And then if they continue forward, they get their A3. Fairly straightforward, fairly simple, but there's a couple of nuances with it that we're going to go through. So first of all, there's variations of that. There's the fact that that loader could be actually going reverse instead of forward. A lot of mining operations will require their loaders in particular to drive with the engine facing forwards rather than the bucket facing forwards. That's because the operator actually has more visibility looking out over the back of the machine rather than the bucket, particularly if there's something in the bucket. So that's really important. Whether the machine's going forwards or backwards shouldn't matter. Overall, that the problem is the same. Whether the pedestrians or the LV are slightly moving as they approach shouldn't matter. And then a really classic variation of this general approach is a workshop or a service bay. As you're approaching that workshop or that service bay, you potentially could be running into people there. It needs to be aware of. A really important consideration, if we look at center screen there, is the fact that our tunnels are not straight. You know, the graphic that I've shown at the top, the animation, we've drawn a nice, perfect straight line, but in reality, tunnels are rarely straight. Mining will follow the ore body, the path of least resistance, as much as possible, because building tunnels is quite expensive. So you want to keep it close to where you're making the money as much as possible. So tunnels are rarely straight. They have lots of kinks and dips and turns. They also are not flat, so they might have crests or dips in it to account for dewatering practices and things like that. So that needs to be considered in how we design solutions for this particular scenario. We also need to give some consideration to what we're calling the knock-on effect, where one machine may push another machine onto a third party. So in the image on the right in the center there, I've got a loader who has hit an LV because the LV is inactive. So the machine's turned off, there's no one in it, there's no passenger. And in some circumstances, that may actually be invisible to the system of the loader. So if it is fitted out with a particular CAS system, it may actually be invisible. But the loader may see the pedestrian and think that they've got plenty of room, so they continue to drive forward and they push the LV onto the pedestrian. So it's something that needs to be considered in this particular scenario. We've also just listed, to prompt people, to get them thinking a bit, some example parameters to consider. And we've done this on a lot of slides, you'll see that, where they're different physical parameters that can affect the way the system works. So for example, the mass of the machine. If the machine is heavier than some sites, than some other operations, you may actually have to brake earlier in order to brake in time to keep your pedestrian in the yellow zone, or even in the green zone, if you will. The operating speed of the machine also has an effect, and the grade of the drive. If you're driving downhill versus uphill, it also has an effect on your braking. So we haven't listed every single parameter. That's not the intent, and it'll probably fill up the entire slide. But we wanted to prompt people and create the conversation that when you're thinking about this scenario, you also need to think about your parameters and how they affect managing this particular scenario, and other scenarios for that matter as well. In our scenario 3, we've got two vehicles approaching each other. So fairly similar to the previous one, fairly straightforward. So both machines, as they approach, they should have their A1 awareness. As they get too close, they get their A2s. And if they continue to drive forward, we get our A3 alarms. Fairly straightforward, fairly easy. Again, the variations, a head-to-head, a head-to-tail, or a tail-to-tail, it shouldn't matter whether the machine's going forwards or backwards as they approach. It applies no matter what. Again, I've listed the example there about the fact that our tunnels are rarely straight in the mining community, and that needs to be considered in this one. And we've also got those flat drives, dip drives, or even crests that need to be considered as part of the design process. And again, those example parameters. This one's fairly straightforward, particularly if you've wrapped your head around the previous one. Now we move into some possible false triggers as a result of those two previous ones. And the first one being congestion. So congestion is something that does occur underground, and in a lot of cases, it's actually quite deliberate. So we've got examples in an underground mine where you need vehicles to queue up or bunch up together to either await for permission to do something or general as part of their job. So if we run a couple of examples to help understand, portal access, for example. So if you've got machines queuing up at the portal to enter the mine, sometimes a lot of mines won't let people in until, particularly after blasting, until they've got all clears. So until the safety inspector or the blasting inspector has been down, checked out the previous shift's blasts, made sure that they've all gone off safely, made sure that the fumes are extracted safely before they let the machines in. So you'll have vehicles queued up at a particular point, waiting for permission to go ahead. Now, in that case, we want vehicles to queue up. Real estate is a premium underground, so we need vehicles to stack together quite tightly in a lot of circumstances. And then once we've got the all clear, once we've got the permission to go, we need the vehicles to actually decongest. And that's particularly important for a theoretical level 9. If we were bunching our vehicles up and we had a level 9 system in play with a slow crawl stop system in place, theoretically all those machines that are bunched up wouldn't be able to proceed. So we need the ability to bunch them up and to proceed in those examples. So we talked about the portal access. We've got go lines, we've got like vehicle parking bays, even a key intersection in a mine, which is what I've depicted on the right there. Sometimes you've got key intersections on declines. You'll see vehicles stack up in a queue waiting for their turn to traverse that intersection. You've also got workshops, maintenance bays, lunchrooms, refuge stations, all sorts of examples where you've got lots of vehicles bunched up together. Then we've got scenario 4, which I think for a lot of operations, this is probably the one of most concern that everyone's really keen to try and solve. And that's a vehicle, a HV vehicle in this particular example, performing a turn into a drive or a cuddy or a passing bay, whatever, where it's occupied by something else. And in this example, we've got a pedestrian or an LV. So here we've got the HV approaching. Ideally, we should have our A1 awareness on approach. And then if the vehicle initiates the turn and starts to transition into that drive, we should get our A2 and our A3 if he still progresses. So pretty important one, and there's lots of different variations for this one, so we're going to go through those. So first up, just on the way that the vehicle approaches, that vehicle could actually perform that turn both forwards and reverse, and it's quite common for both of those to occur. Sometimes the vehicle will actually drive past the intersection and then reverse in. That's the ideal way. And then there's a set of eyeballs looking into the bay. But a lot of the times it doesn't happen. They have to perform the turn straight in. And that can be bucket forward or it can be engine forward in the case of a loader. But with a truck, it can also be tub forward in or it can be engine forward. So that needs to be considered. If there's a pedestrian in that bay and he hears a loader coming, the pedestrian won't be standing still. I'll guarantee it. If they hear a machine coming, they'll be moving around trying to get to the edge of that bay to make sure that they're not in the way of that loader if the loader makes the turn in. So we need to consider that things may be moving in that bay and how we make sure that we still sense that fact. And I've shown a nice clean T there, but it can also be a cross intersection or just a simple sharp turn. It can occur. If you've got a plain 90-degree left turn coming up, you could have another vehicle also wanting to perform that turn in the opposite direction. And you're really blind to that vehicle from a visual point of view until you actually start initiating the turn. So that needs to be considered as well. The images in the center down the bottom, what I've tried to show here is that vehicles can already be turning prior to the turn. So on the left, we've got a left turn, a gradual left turn before performing a full left turn. So that's really important for any of the technologies that are looking at like a bending beam technology or something like that. You may already be, the operator may already be sending a turning signal to the machine prior to the actual turn, just following the tunnel in general. And the opposite can occur too, which is the next image to the right, where we've got a gradual left turn before a full sharp right turn. And that's quite common, particularly on decline. So you might be driving down the decline in a corkscrew fashion, heading down the mine, and you might hear another vehicle coming up towards you. You need to do the opposite turn into a passing bay to allow that vehicle to pass you. So that's actually quite common, that particular example. We also have the fact that our turns, our cuts or our parking bays are rarely perfectly 90 degrees. Ideally, we do want to do that from a construction point of view, particularly from a ground support point of view. A perfect 90 is a lot easier to maintain ground support on. However, sometimes certain circumstances require a more acute angle of your drive coming off your main drive. So you can have some very sharp corners. I've seen plenty of operations that have required a multi-point turn to actually traverse a full turn because of the sharp corner. They do exist. They're not as common as the other examples, but nonetheless, they're there. So we need to consider those really acute angles as part of our turn in our design process. And because we've got that acute angle, we also need to consider that when the traffic is going the opposite direction, it can actually transition to a merge rather than a stop and turn. So that also needs to be considered as part of the design process. Some additional example parameters there just to prompt people and make them think about it is the turning speed of the machine. I've spoken to a lot of operations that have got this problem sorted out quite well because their operations are quite tight and they have very limited speed in their operations, so 6 kilometers an hour, 7 kilometers an hour. But when you're running some of the bigger operations with your bigger machines, they'll probably have a crack at some of those turns at 20 or even 30 k's an hour. They'll do it in second, maybe even third gear. So it's something to consider is the turning speed, not just the way the machine turns when you turn the steering wheel, but also the speed at which they will perform the turn also needs to be considered. So like I said, very, very hot topic, this one. Lots of people are interested in this one, as well as the next one, which is the possible false trigger for the turning scenario. And in this case, we've got the same setup. We've got the LV pedestrian in the bay. We've got a HV approaching. However, in this particular instance, the HV intends to drive straight past, so that they're not going to perform the turn. So here again, we should have a A1. However, if the pedestrian on the LV is potentially too close, we could actually get an A2 or an undesirable A3 in this particular example. Now, if this was a level 9 system, theoretically, that would be a crawl or a stop command. So that machine would come to a stop because that pedestrian or that LV was there, even though there was no collision pending. And this is quite common when you've got particularly an LV. If we focus on an LV for a moment, if you've got an LV at an intersection waiting to transition that turn, they don't park well back from the intersection. They actually park quite close to the main drive because they need to use their eyeballs to look around the corner and see if there's a machine there. So they do approach quite closely and wait or check and wait before they perform the turn. So there are a lot of close interactions there, even though it's not a pending collision. Once again, we've got the different types of turns. So you may already be doing a gradual turn as you approach that cutty. So you might be turning left before the left side cutty, even though you're driving straight ahead. So you're telling your machine that you might be turning left. So if any technology that uses that input from the steering wheel needs to consider that. And the opposite can occur too. You could be doing a full left turn and the cuddy could be on the right-hand side. So, probably less of a problem, but still needs to be considered. Another variation of this, of driving past something, is our crib rooms. So, I mentioned it previously. You've got crib rooms and workshops. You're driving straight past them. You're not intending to turn into them. They're not exactly a bay designed for a HV. But nonetheless, you've got lots of people there, and whatever the technology is using, be it a cap lamp sensor or whatever, there will be lots of sensors there telling machines that, hey, we've got people or we've got other vehicles parked here. Perhaps you should have an A2 or potentially even an A3, depending on how sensitive you are. So that needs to be considered. That's a real world example there, the crib room that I've drawn there. That's probably where I've got those helmets drawn. It's probably about 5 to 10 meters away from a main haul route. There's a door in between, but nonetheless, you've got lots of helmets. In fact, they stack the helmets at the doorway before that, and we have HVs driving past. So that's a real world. The other one that we wanted to capture and discuss is our safety bays. That particularly in Canada, we have a lot of Canadian operations that have these, where they've got cuddies installed on their drives, big enough for personnel to retreat into if they see HVs coming. So we need to consider how we manage those. Some operations may want that alarm. They may want an alarm to occur even though the pedestrian is inside that cuddy and trying to move to a safe place. Whereas other operations may actually want it to be silenced because the person is actually safely in that bay. So it needs to be considered. It needs to be discussed with the individual operations and with the suppliers, right? Fairly straightforward, but this one in combination with the previous one, I think is one of the biggest ones the underground community is really interested in. And we've got our passing bay, slight variation on the T-intersection that I've shown previously. These are deliberate passing bays typically for HV vehicles, and they're usually installed on declines or on haul roads. You don't normally see these out in the ore body. So this is where you got lots of HV traffic usually, and you don't make the entire tunnel wide enough for 2 vehicles to drive down. You make it wide enough for one, and then you put passing bays in stages along the drive. And those passing bays are typically big enough for 1 vehicle. However, I have seen passing bays where you can jam in multiple vehicles. And I've seen a lot of examples where you'll have a HV in there and then a couple of LVs will sneak up behind and they'll jam themselves in there to allow another HV to pass. So it can get quite congested. So once again, though, this is not a collision, right? So we're not predicting a collision here. We're intending to drive straight past, but we do have the potential for false alarms to occur. And again, if we were a theoretical level 9 operation with some sort of slow crawl stop solution in place, this would halt the operation. Now, the image below in the center below with the 2 arrows, that's a real world example of a passing bay. You can see that it's barely big enough. You can hardly tell the size of the flitch in the side of that drive. But that flitch, I can tell you, is big enough for two trucks of the order of around 55 tonne. So you can fit 2 roughly 55 tonne size vehicles in that side by side, and you'll have pedestrians that could walk down there. They wouldn't be able to stretch their arms out, but they might be able to get their elbows out and touch both machines. So they're quite close, right? The 2 machines are very close to each other. One will be driving at speed, 2nd, 3rd gear. The other one will be parked up waiting for that vehicle to drive past so he can traverse back out into the drive. So it needs to be considered as part of the design process. They are rarer than the T-intersections that I talked about, but nonetheless, they do exist. Right, the next failure mode is where we're deliberately wanting to approach another vehicle. And there's loads of examples of this one, which I'll go through, but the one we're visually going to show is a loader approaching a truck. The intent here is that the loader would have ore and they're loading the truck, right? They're filling the truck up with ore. So this is an example of a trigger or an alarm that we don't want in the industry, right? We need this particular activity to actually occur, and we don't want to generate alarms in it. So here, if we didn't have a solution for this in place, we'd have our A1 on approach, and then theoretically we'd trigger an A2, and if we got too close, we would trigger the A3. Now, if this was a level 9 operation, that loader wouldn't even be able to unload the bucket. They would be halted prior to even reaching that truck. So that's, I guess, why we're looking at it. So As I said, lots of examples of this one. We've shown the LHD loading a truck. There's also an agitator transferring to shotcrete spray rigs. So the picture in the center below is a picture of, unfortunately I couldn't get one underground, but it tells the story quite well. We've got an agitator there unloading concrete onto a spray rig, and they're spraying a portal entry there. So we've got two different machines. Granted, one is sitting still, it's not moving, but nonetheless, you've got two mobile machines there deliberately wanting to approach each other. You've also got other examples like service vehicles that need to come down and do a service on a HV. You've got a fuel truck. A lot of operations run a fuel truck rather than having a fueling bay. So you'll have a big truck rock up at the HV, wanting to fuel it up, needs to get in close enough to actually have the hose reach. You've also got examples where a HV will need to reverse and hook up and tow another HV. Happens quite a lot. So that needs to be considered as well. Also, there's different variations of how that can occur. So we've shown a nice, loading a truck on the side, but we actually do load trucks from the rear as well, so end to end. And we do have examples where the loader will have to reverse past the truck has to move forward to get in front of the loader will then dump, and then the truck gets out of the road, and then the loader goes off and picks up another load. So there can be a bit of a ballet of movements occurring to actually do the loading, depending on the real estate that's available at the load point. So that needs to be considered, right? So don't assume that the second vehicle, the truck in this case, once it sets up, it just sits there and doesn't move. Sometimes they actually have to move as part of the activity that's going on. And then the other one that needs to be considered is a truck loading bay. So there are many operations that love these. Wherever they can get the funding to do it, they will do it because it has a significant benefit to their operation. So a truck loading bay is where you can load a truck at different grades. So the truck will physically be slightly lower than the loader. The loader will be on a higher level, only the height of the truck. But it makes a big difference to the loader because the loader doesn't have to lift its bucket up to dump the load. So it actually improves the cycle time. You go faster. So you'll see these in operations that have quite a lot of mucking activities to occur on a certain level that justifies putting the truck loading bay in. So they are quite common. They're not everywhere, but they do exist. But it's some important things to consider there. So where there is that loader and that truck arrangement, there'll be a stop log. So there's no risk of the loader driving over into the truck. And the loader's tram will be barricaded. They'll have a dedicated barricade up so no one can enter the loader's tram. That's typically what we would see in the industry. However, the truck loading bay will be usually installed on a decline. So where the person who has taken this photo is standing, they'll probably be standing on the decline itself. We tend to put truck loading bays out near the decline. That allows the truck to be loaded and then jump straight onto the decline and off they go wherever they need to deliver it. There's various reasons why we do that. Probably the main one is it allows you to have really big trucks with small loaders. If you want to send a big truck out where the loader's currently going, you've got to make all your drives really big to suit the truck. Whereas if you keep the truck on the decline, you only have to make the decline big enough. So it's a pretty big cost-saving benefit if you can pull it off. Because we're on the decline, though, we have other traffic driving past. So in the image there beside the photo, I've shown an LV driving past. We still need that activity to actually occur. So one, we want the truck to be loaded safely and efficiently, and we also want other vehicles to be able to drive past in this particular circumstance without being interrupted. If that was a HV in the place of an LV, they will be probably close enough for sensors to detect, so we don't want that A2 or that A3 in that particular circumstance. But these are sort of things that need to be considered there as well. Last couple of sets looks at hazards. So hazards, we've captured quite a lot of different things in hazards. So we'll go with the void as the example. We've got a void, we've got a vehicle approaching a void here. If they get too close to that void, we get our A2. And if they continue to drive forward, they get our A3. But our voids are not our only hazard. We have quite lots of different hazards. Voids and unsupported ground are by far the most common. And they're usually managed quite well by the operation with a rather large earthen barricade to make sure that the machine doesn't drive off. But they do occur, and some operations may want to address this in their particular risk matrix. So it needs to be considered as a possible problem and look for solutions. We also have other variations of hazards. So we talked about voids and unsupported ground, but we've got things like sumps. So lots of operations won't barricade their sumps because they're concerned about some of the smaller vehicles driving into the sumps and and getting immersed. And we've also got critical infrastructure such as an electrical substation. The last thing we want is a loader driving full barrel into a transformer or electrical substation. It'd be quite a catastrophic collision. And then we've got the more temporary installations such as a diamond drill. A diamond drill might be set up in a crosscut, and they're not there permanently. They're there for maybe 2-3 weeks depending on the campaign. They'll set a barricade up. So they're not a normal thing that the loader operator would see every single day if they were working the same area. It might be something new, something abnormal. So those are the sort of things that some operations may be interested in trying to sense and therefore notify the operator that, hey, you've got a hazard here you need to be aware of. For the stoping operations though, what must be considered is that there are lots and lots of voids, particularly in stoping operations, not necessarily in block caves or pillar operations. In stoping, there are loads and loads of voids scattered throughout the mine. So whatever technology we do develop for this particular problem, if a site is keen to solve it, the technology needs to be numerous in itself, right? It needs to account for that fact. So the image I've got there, that's a drive. Each of those cross cuts may be 20 or 30 meters separating from each other there as we go up the page. And that drive heading up the page might be another kilometre, maybe even 2 kilometres beyond what I've shown there in the drawing. So they are extensive, and that's just one level. There might be 20 or 30 levels in that operation. So there are a lot. They do exist. And as I said, most operations deal with it with an earthen bund, but some operations may be looking at technology to try and solve this one. So it's worth discussing and understanding if solutions are available. However, there is a variation to this, which is the false alarm, and that's where we deliberately want to approach that hazard. So in the case of the void, we deliberately do approach voids to tip into. So where we've emptied a stope, we will tip waste material into that stope to fill it so that we can take the next series of stopes around it. So it's important for ground stability that you do fill it. So I mentioned previously that we do have lots of voids, and that's not because the operation is lazy. It's because they're constantly emptying new stopes, filling them up and so that they can take more stopes. So it's like a sequence, a big cycle that's going on. So you do have activities where you deliberately want to approach that void or even dangerous ground, such as unsupported ground, to perform a particular activity associated with that hazard. So in the case that on the animation we've got here, that stope or that void will have a stop log there, and the loader will drive up onto that stop log and they will tip their load, which is the picture in the middle there. That's a typical stop log. So in this case, we don't want the alarm to occur because there'll be multiple tips per hour, per day on this particular example. So we don't want to be generating nuisance alarms in that particular case. There's other examples of what that could be. We've shown a stop log. Sometimes it's a grizzly, so you can actually drive on top of the void. It could be the unsupported ground, so you could have a jumbo approaching unsupported ground in order to set up and do some ground support work. It could even be a loader mucking out a sump. So a lot of operations will only allow a loader to enter a sump, and that's so they can muck out all the fines, all the mud that's built up, or the shotcrete fibres that are washed in, depending on the operation. So sometimes we actually need to deliberately do that. Again, though, like the previous one, if the operation does want to address it, they can be numerous, and they can also have a short time life. So an operation tries not to leave their voids open for very long, because it may hold the sequence up on another stope that they want to take down the track. So they try and fill it as quickly as they can. And as a result, the stop log may only be sitting there for a matter of days, maybe weeks. It's rarely years for a temporary fill activity. So the technology needs to account for that. It needs to be easily deployed, easily retrieved, easily redeployed as that stop log is used on that particular job and then relocated to another job to get that stope done. So that's something that needs to be considered as part of the design process. And then the last one is an example of a failure mode where infrastructure or mobile equipment could actually affect the sensoring capabilities on the mobile equipment. So this is, some failure modes that have been seen in the industry, and we'd really like, the industry as a group to work through and solve this problem. So in this case, we've got a HV driving past a transformer or a high current cable, and the sensors potentially have been compromised by that infrastructure. They've been adjusted, they might have been disrupted, whatever it may be, and you have the potential there to not see another hazard, i.e. the pedestrian in this particular example. So there's lots of different examples of that. I've put a lot of images in here around electrical. We're not saying electrical is the sole cause here. It can be iron. So you could have a lot of steel infrastructure underground. That picture there's a truck loading bay where they load a truck from an ore pass. So there's lots of steel infrastructure there. Are sensors susceptible to that steel? Not too sure, but we want it to be questioned and considered as part of the design process. We've got the electrical one, so lots of high current, potentially generating magnetic fields there, depending on how the site has set up their electrical. Typically, they try and keep the magnetic fields to a tight frame because it has influence on other things. And then we've got the new one, which we're really interested to see how it progresses. There's not a lot of data on it, and that's our battery electric or hybrid vehicles. So how is technology going to work and perform on our battery electric vehicles in particular? A lot of people, we're keeping a close eye on this one because obviously with battery electric, you potentially lose one of your sensors because you've now lost your hearing. It's quite quiet compared to a big diesel engine roaring up the drive that you can hear from quite a long way away. You've got a much quieter vehicle. So you've got the potential of the vehicle sneaking up onto you. So it pushes more into the importance of how technology can play a part. So this is something we're really keen on understanding. So again, potential failure mode, want the industry to consider it, look at solutions that can help the industry shift forward on it.